Imela, let's quickly do number systems, and I'll start with basic definitions. Let's start by explaining or defining the number system for number sets we've got. I'll start with natural numbers, and the scientific notation for natural numbers will be n. These are just numbers that we feel natural to count from. For instance, 1, 2, 3, 4. Now, those numbers it's just natural for us to count from one and say this is one cell phone, got two cell phones. So it's basically just natural for us to count from one. Obviously, the number represents the quantity in this scenario. That's why when it comes to natural numbers, we also say that they are counting numbers. They are also called counting numbers. And whole numbers are just natural numbers, but you add zero to them. So immediately when you add zero, which is nothing, basically zero is a number that explains or measures nothing. And in any field, nothing will be zero, right? So that's why when people criticize you or people brag about certain things that mean nothing to you, you normally say they're bragging with a zero, coming with zero. It's because zero is nothing. That's what it means. All right. And with whole numbers, you just take your natural numbers and you add zero to them. So it's just your natural numbers. You just have to take your natural numbers and add one number, which is zero. That's what whole numbers are. The next number set will be integers. Integers are just whole numbers plus negative natural numbers. So you'll notice that these are whole numbers. So in whole numbers, we will have natural numbers, and then finding the negative natural numbers, that will give you a whole new set, which will be your integers. So your integers in scientific notation will show them as Z. So this here represents integers. Integers is just your whole numbers plus the negative natural numbers. Now, when I get here, I normally start asking my students as to between -5 and -1, which one is bigger? You might be tempted to say that -5 is bigger. Please note that when you're dealing with natural numbers, the far left natural numbers, or the numbers that are, when you're dealing with negative numbers, sorry, did I say natural? When you're dealing with negative numbers, the numbers that are furthest from zero are small, and the numbers that are close to zero are the bigger ones. Because -1 is bigger, is closer to zero, it means that it'll be bigger than -5. Same, -1 will be bigger than -100. -3 will be bigger than -1,000. Okay, that's what it means. Then we'll have rational numbers, okay, represented as Q. What are rational numbers? These are numbers that can be expressed as a fraction. This includes all finite and recurring decimal fractions. I will start by explaining what a fraction is. A fraction has a numerator and a denominator, where denominator can be any number except for zero. And highlight that the denominator cannot be equal to zero. However, the numerator can be any integer. Same with the denominator. It can be any integer except for 0. And these are examples of your rational numbers. 3/2, that is a rational number. What type of fraction is that? Is it a common fraction or improper fraction? Find out. The square root of 9 is just your natural number or integer whole number, because the square root of 9 is just 3. The cube root of 27 will be 3 as well. Okay, so basically all of those can be natural numbers or integers or whole numbers. Then we've got negative square root of 144. So when you find the square root of 144, you will notice that the square root of 144 is actually 12. But this is the negative square root, so it will be negative 12, which is an integer, so that can be a whole number, obviously. Then we've got 0.7 recurring. When you see that dot on top of 7, you must just know it can be written as 0.7777777. So it's recurring, and a recurring decimal is a rational number. It can be written as a fraction. A fraction has a numerator and a denominator. Okay. Then we've got irrational numbers. Irrational numbers, these are numbers that we cannot express as a fraction, meaning that they cannot have a numerator and a denominator. So non-recurring decimals are classified under this set of numbers. And these are examples here. When you put in the square root of 3, what do you get? You see, it gives you an irrational number, right? Then we've got real numbers. What are real numbers? Real numbers includes all the number sets. That can be your natural numbers, whole numbers, integers, rational numbers, and irrational numbers. So basically anything that is numbers will be part of your real numbers. And as I've said here, for real numbers, the scientific notation will be R. Then we've got non-real numbers. These are numbers that do not fall under any of the numbers that we spoke about. And I know when you ask students what are real numbers, they'll normally say it's numbers that are not real. That is true, but when I ask for the explanation, I need you to explain what they are. So basically, these are numbers that we cannot classify under any of the number sets that we have done. We cannot classify them as real numbers. We cannot classify them as natural numbers. We cannot classify them. So any number that cannot be classified under the number sets that we have done is non-real. They, as I've said, they do not form part of any of the number sets done that form. For instance, you're going to have the square root of -4, which will normally be -1 in numbers. We call it a complex number or imaginary number, is regarded as I squared. So when you find negative square root of 4, that is basically 2i. Okay, it's 2i because negative is I squared. 12, -12, that'll be the square root of 12i and infinity. A lot of people think that infinity is a number. No, it's not. And any of the variables that we normally use to represent numbers, unless it's clearly classified what the variable represent. Okay, so all of these will be your non-real numbers. And you will notice that under real numbers, which is this yellowish or gold rectangle, any number that falls within that yellowish or gold rectangle, we call it a real number. So under real numbers, we have natural numbers, whole numbers, integers, rational numbers, and irrational numbers. There's one question that I like asking. Can rational numbers be natural numbers? Yes, they can be. But can natural numbers be rational numbers? No, natural numbers can't be rational numbers because under rational numbers, you also have integers, negative numbers, and negative numbers can't be natural numbers. So it means that we can't, natural numbers, under rational numbers, we have natural numbers, but under natural numbers, we cannot have rational numbers. I hope that makes sense. All right. Here you just need to complete the following table by ticking in the appropriate columns to which each number belongs. All right. Can I say -2 divided by 3 is a natural number? First of all, that negative throws out. So because of that negative, it cannot be a natural number, it cannot be a whole number. Can it be an integer? It can be, because an integer is a combination of negative natural numbers plus whole numbers. And there are no fractions there. Because of that fraction, it cannot be an integer. However, it can be a rational number. And since it's a rational number, rational numbers also fall under real numbers. That means it'll also be a real number. What about 0? Can it be a natural number? No, under natural numbers, we don't have 0. 0 will start with your whole numbers. So it actually makes your whole numbers, right? You put a hole in it, you take your natural numbers, put a hole on it, and then you'll have whole numbers. Okay. A whole is basically 0 in this sense. All right. Can be an integer and can also be a rational number. The fact that it's a rational number, it means it cannot be irrational. So it'll also be a real number. What about the decimal 0.33333? That is a rational number and a real number. The square root of 27, you'll realize that it gives you a non-recurring decimal. So that is irrational. And the fact that it's irrational, it can also be a real number. Square root of 4 divided by square root of 9, that is 2/3, which is a rational number and a real number. Cube root of 8 is 2, so it can basically be all those numbers except for irrational. -1,7 is a finite or finite decimal, so that is a rational number and a real number. 111 is all those numbers except for irrational numbers. Okay, so far so good. All right, let's go back to the definitions and talk about the property of 1 and 0. And I'll start with the identity elements. So 0 is the identity element of addition because anything you add with 0 will be that thing. Right? So if you take 4, add it with 0, it's still 4. If you take m, add it with 0, it's still m. If you take u and add u with 0, you are still u. You don't modify yourself in any way. And we say that 1 is the identity element of multiplication because anything you multiply with stays the same. 1 multiplied by m is 1. 1 multiplied by a million is still a million. 1 multiplied by 2 is still 2. So that's why we say 1 is the multiplicative identity. Now let's go to inverses. I'll start with additive inverse. Additive inverse is basically negative. If you don't add, you subtract. If you don't multiply, you divide. If you don't subtract, you add. If you don't divide, you multiply. So those will be the additive inverses. So if you take a number and add it with its additive inverse, it'll give you 0. Guys, that is very, very important for when you do algebra as well as calculus when you get to varsity. It's very, very important. You need to understand that for something to be an additive inverse of the other, when you add the other with its additive inverse, it should give you 0 all the time. And what is the additive inverse of 4? What can you add with 4 to get 0? You can add 4 with negative 4 to get 0. So negative 4 will be the additive inverse of 4. And what is the additive inverse of negative 8? The additive inverse of negative 8 will be 8. Let's go back and start with multiplicative inverse. The multiplicative inverse is a number multiplied with a certain number that will result in you having 1. For instance, what can I multiply with 3 for me to get 1? I will need to multiply it with its inverse, which will be 1 over 3. So from this, we can conclude that the multiplicative inverse of 8 is 1 over 8. The multiplicative inverse of 3 over 7 will be 7 over 3. You just swap the numerator and the denominator to get the multiplicative inverse. Note that any number in maths, if it's written as it is, it's always divided by 1. So this 3 here is divided by 1 because any number divided by 1 is still that number. So that's why when you swap the numerator and the denominator. So if you have 3 over 1, when you swap them around, it will give you 1 over 3. That is why we say the multiplicative inverse of 3 is 1 over 3. Okay. And the multiplicative inverse of 5, how much will that be? It'll be 1 over 5. What is the multiplicative inverse of 2 over 3? It is 3 over 2. Great. Let's move on. Now, the multiplicative inverse or reciprocal is the number multiplied with a certain number and she'll give you a result of 1 as I have specified. So if I was to take 5 over 1 and multiply it by 1 over 5, I will get 1. And if I have if I have 2 over 3 and I multiply it by 3 over 2, that'll give me 1 as well. Okay, so basically if I have this, recording in progress. So for this one, I will have 1. Okay, so the answer will be 1. So that's how you check if the multiplicative inverse is actually correct. Let's try 5. So this one will also be 1. It's just that, guys, I remember teaching this one student when I was in my home school, Kenneth Masigela. And I think this boy went to UP to study maths or finance or actuarial science. I don't know. Or is it economics? I'm not sure. But I think it's related to math or finance. And he kept on saying that to succeed at varsity, you have to forget about what you learned in high school. And I'm like, look at this boy. Okay, I can't say dummy. Look at this boy. And he is at varsity doing high level math, and he can't even see the link that some of the things, not some, all of the things that you're doing at varsity, you did them in high school. And I know the lecturers have this tendency of telling university students to forget about what they learned in high school. I don't know why. Because this year, if I have five, and the thing is, most of us that are teaching in high school, we did BSc in math. I did BCom. So basically, I know what's happening. All right. Um, I know what is happening in accounting, but you'll find my accounting student when they get to varsity, they're told to forget about accounting that they learned in high school, which is weird. I don't know if anything changes. Does an asset now change? It's no longer a resource we use to generate money. Is it something else at varsity? Doesn't an asset increase on a debit side? Is it something different at varsity? And that's where I get perplexed. I mean, we know that depreciation is an imputed expense. Does it change when it gets to varsity? Same thing. The reciprocal, multiplicative, reciprocals or inverses, we do them at varsity. It's just that at varsity you are now using matrices. You know, you're dealing with this matrix, the inverse of this metric, multiplicative inverse of this matrix will be 1 divided by whatever. All right. So, which is a little bit weird when you are told to forget about what you learned in high school. And I wish I had a very good math teacher in high school. Um, I'm not saying that my math teachers were not good, but I wish I had gained a lot. And I wish I had myself in high school. That's why I tried to be the teacher that I didn't have when I was in high school. Don't forget these things. They are very, very important. And if you remember them now and you learn them now and you know them now, trust me, guys, you'll never go bad when you get to varsity. It is just a revision. Varsity is just adding to what you have already learned. It's nothing new at all. It is nothing new at all, contrary to what is being said out there. Okay. Let's move on to other properties. I'll start with commutative operations. So commutative operation simply says that my English data is running out today. The order of addition doesn't matter. You will still get the same result. And that's what I will start with. So if I take 3 and I add it with 2, how much do I get? You'll get 5. What if I take 2 and I add it with 3? You still get 5. And 3, add it with 2, you still get 5. Do you see that the order of addition doesn't matter because you still get the same answer? That's what it means. So if I have m plus n, it'll be equals to n plus m. If I've got 3 plus 7, it'll be the same, which is 10. It'll be the same as 7 plus 3. What is the commutative inverse of a plus b? So that'll be b plus a. What is the commutative inverse of 2 plus 3? That'll be 3 plus 2, which is 5. Okay. And then we've got associative property, which says that if I have 5 plus 4 plus 1. I can start by adding 5 plus 4, which is 9, and then add 9 with 1 and get the same answer as when I add, which is 10, obviously. I'll get the same answer as when I add 4 plus 1, which is 5, and 5 plus 5 will be 10. Okay, so I can group add 4 plus 5 and then get the answer and then add 9 with 1, which is 10. Or I can say 5 plus, just start by adding 4 plus 1, which is 5. So 5 plus 5 will give me 10. Or I can add 5 with 1 first and then get the answer, which is 6, and add it with 4, which is 10. So basically, you can start by adding any numbers for you to get to what you need. All right. That is what we call the associative operation. To associate means that you are grouping, you're associated with a certain group. So when you associate associative property, it says that you can group certain numbers and the order of the grouping does not matter. The order of the grouping does not matter. Okay. So it applies as well with multiplication. The order of the grouping in multiplication does not matter. For instance, if I've got, let me just put it in numbers, because when I put it this way, it'll be a little bit complex for some of you. So if I have 3 times 2, and then times this by, let's say, 5, all right? I can start by grouping these two, okay, which will give me 6. And what is 6 times 5? 6 times 5 will give me 30. Okay, so you can group it that way, or you can start by grouping it this way. Okay, and that was 30, sorry. So here I can say 3 times 10, which will still give me 30, right? Or you can group it this way. Guys, math is awesome. Math is awesome. Or you can group it in what way? Or you can group it this way by taking 3 and multiplying it by 5 first, and then multiply it by 2. So when you group it this way, you multiply this 2 first, which will give you 50, and multiply that by 2, which will give you 30. Okay, so that will give you 30. That's your answer. So the grouping does not matter when it comes to addition or multiplication. Now, I want you to group this in different ways. You can start grouping them by grouping 2 and 3, or grouping 5 and 3, or grouping 2 and 5. See? Let's move on. Distributive operation. Now we're doing more advanced math, and people forgot these basics and they think we are doing them for the first time. So in this way, when you distribute, especially when we're dealing with one term, we say it's a monomial, and we're dealing with 2 terms or more, we call it a binomial. So when you are multiplying a monomial with a binomial, we'll take the first term inside the bracket and multiply by the outside factor, which is p. And the answer here will just give you MP Mpumalanga times PN, all right? So it'll be PM times PN. Similarly here, if I've got this, I'll just start by multiplying P with M and multiply the same P with N, and that'll give me PM minus PN. So the sign in the middle will only change if the factor that you're multiplying by is negative. Okay, it'll only change if the factor you're multiplying by is negative. But for as long as the factor that you're multiplying by is positive, the sign inside the bracket will not change. I hope you're good. All right. Now distribute this here. It'll give you 5 times 2, which is 10. 5 times 3 is 15, and 10 plus 15 will give you 25. What about this one here? 4 times 10 minus 4 times 3. That'll give you 40 minus 12, which will give you 28. What about this one here? It'll be 5 times x, which is 5x, 5 times 2, which is 10. So you'll have 5x plus 10. Alrighty, let's move on and deal with factors. What are factors? Factors are numbers or terms multiplied to get a product. So when you multiply factors, it can be two. You can have one factor, it can be two factors or more. You will get a product. Product is a multiplicative, is the result of multiplication, which is multiplication of factors, all right? Now, what are factors of 10? Which numbers can you multiply, or how many numbers can you multiply? Different numbers you can multiply to get 10. The first one will be 1 and 10. It'll give you 10. Okay, the other one will be 2 and 5. It will give you 10. So the factors here will be 1, 2, 5, as well as 10 itself. So those are the factors, numbers that you can multiply to get the product, which is 10. Which is, 10 in this case. It'll be written as the factors of 10 will be 1, 2, 5, and 10. So you multiply 1 with 10, you get 10. You multiply 2 and 5, you get 10. So that's why all of those are factors. What are factors of 20? It's 1 and 20, 2 and 10, 5 and 4. So it'll be 1, 2, 4, 5, and 10. As well as 20. How did I forget 20 then? Okay. What about this one here? So what will be the factors of 16? Factors of 5, factors of 32, factors of 15 again. Oh, it's 15, it was 16 before. Factors of 28, factors of 12, factors of 7, factors of 36, and factors of 11. Do that quickly. Press pause and then play. So these are the answers that you will have. I want you to pay attention to the second point, the factors of 5 and the factors of 7, as well as the factors of 11. You'll notice that for 5, 7, and 11, math is awesome, guys. They only have two factors, which is the number itself and 1. Such factors or such products, we call them prime numbers. So prime numbers or prime factors or prime number has only two factors, which is 1 in itself, okay? So you will notice that for factors of 11, it's 11, and which is itself and 1. Factors of 7 is itself and 1. Factors of 5 is itself and 1. Factors of 3 is 3 itself and 1. Factors of 13 is 13 itself and 1. So such numbers or products, we say that they are prime factors or prime numbers, okay? So actually prime numbers, not prime factors. Prime factors, it's where the factors of a given product are just prime numbers. And we'll talk about that shortly. Let's go to multiples. This one, guys, it's easy. A multiple is basically a product of a number multiplied by natural numbers. Like 5, I can multiply by natural number. So it'll be 5 times 1, which is a natural number, 5 times 2, which is a natural number. So it's 5 times 1, which is 5. 5 times 2 is 10. 5 times 3 is 15. So basically, we say that those are the multiples of 5. It'll be 5, 10, 15, so on and so forth, all right? And we've got multiples of 6, obviously, will be the products derived by multiplying 6 by natural numbers. And that'll be how much? 6 times 1 is 6, 6 times 2 is 12, 6 times 3 is 18. And you will notice that we're just taking 6 and we're multiplying it by these over here are just natural numbers. And the answers we get, those are the multiples. So multiples are just a product of a given number multiplied by natural numbers. So this will be written as 6, 12, 18, blah, blah, blah. Okay. And then we find factors of 20. What are they? So 20 times natural numbers. I stopped at the third natural number. The question will be specific as to which natural number you need to stop at, because you can't write all of them. It'll take you the whole period. Okay. We good? Great. So this will be 20, 40, and 60. What about these ones? What do you get as the answers here? Okay, these will be your answers. I think I spoke about this one earlier on, what prime numbers are. As this is key, as I've said, these will be your prime numbers. There's more to that. So it's just a number that has two factors, which is one in itself. I have spoken about that. That's why for all of these are prime numbers. Factors of 17, it's 17 itself and one. So if you multiply 17, I mean 1 times 17 itself, that'll give you 17. Please don't judge, okay? I'm not using, what do you call whatever pad here? I'm using my, is it a Kesa? Yes. It's kind of hard to write using a Kesa here. Okay, I wish I was using a writing pad. Okay. Now, all compound numbers are all natural numbers with more than two factors. And what are those? It'll basically be these ones. We have 4, 6, 8, and 9. They have more than two factors. We have done factors. So factors of 4 will be 1, 2, and 4 itself. Okay. So it has more than two factors. 6 will be 1, 2, 3, and 6 itself. So any number that has more than two factors, we call it a compound number. Okay. And I think we spoke about all of that. Okay. What are the factors of 20? It'll be 1, 2, 4, 5, 10, and 20. And which of those are prime numbers? It'll be 2 and 5 from what I see there. Now we're going to be determining the prime factors given a product. The key here is for you to take the product that you're given and always divide it by the lowest prime number. Lowest prime number. What is the lowest prime number that you can think of? So you'll go back to those prime numbers and you notice that the lowest is 2. So if 2 doesn't get into the product that you're given, the lowest will be 3. If 3 doesn't get into the product that you're given, the lowest prime will be 5. You always divide by the lowest prime. Lowest prime. I'm emphasizing that, guys, because it's very, very important. Let's have this one. So which lowest prime number can get into 16? It is 2. 60 divided by 2 will give you 30. The lowest prime that gets into 30, it is still 2. And 30 divided by 2 will give you 15. Lowest prime that gets into 15, is it still 2? No. So what comes after 2? It's 3. Can 3 get into 15? The answer is yes. And that will give you 5. Now, is the lowest prime that gets into 5 still 3? No. So what comes after 3? It is 5. That's why we will use 5 here. And 5 divided by 5 will give you 1. And all these prime numbers that we divided by, we call them prime factors. So you will write them as a product. Now, to write them as a product, you will write it as 2 times 2 times 3 times 5. Now, when you multiply the bases that are the same, please note that you write it as a single base, and the exponent will be the number of times you multiply that base by itself. The exponent is basically a number that we put right there, which tells us how many times a base has been multiplied by itself. So we can write that as 2 squared times 3 times 5. That is because this 2 tells you that this base here has been multiplied by itself twice. So the exponent tells you how many times the number has been multiplied by itself. Okay, prime factorize that. What will it be? Divide by 2, you will get 6 divided by 2, you will get 3. Now my prime number can be 2 anymore. It'll now be 3. So when you write this, it'll be 2 squared times 3. Easy, right? Easy peasy lemon squeezy. All right, let's do this one quickly. What are you going to get here? It's 5, it'll give you 7, and then it becomes 7. So here, your prime vectors will be 5 times 7, which will give you 37, okay? And I gave you that as a classwork. You can try it out. Try all of them. Write them down, and you can email them to me so that I can check if you got them right, okay? Okay, I did some. Which was the first one, and the second one will be this. Okay. So the thing is, guys, when I gave you the classwork, you needed to stop there, do all of them, and then press play. Okay, don't just check the answers or how I did it. Do it first before you check the answers. Okay, that's how you learn so that you can see where you made mistakes. Try this one out. I'll give you like 2 minutes. I already did the first one. So this is what I did in my support lessons. All right. Try that one. Give yourself 3 minutes. Press pause. Now, after you've given yourself 3 minutes, you can press play. Now, please check out for part 2 and probably part 3 of this as we revise everything we have done this year. Kgotso.